Assalamu alaikum. Today I will follow the lab 3.7, which is the hyperparameter tuning. For the overview, this lab is a continuation of the guided labs in module 3. In this lab you will construct a hyperparameter tuning job to tune the model that you constructed previously. You will then compare the metrics of two models. Introduction to business scenario. You work for a healthcare provider and want to improve the detection of abnormalities in orthopedic patients. You are asked with solving this problem using machine learning. You have access to dataset that contains 6 biomechanical features and a target of normal or abnormal. You can use this data to train an ML model to predict if a patient will have an abnormality about this dataset. This biomedical dataset was built by Dr. Henry Q and et al. This data has been organized in two different but related classification tasks. The first task consists in classifying patient as belonging to one of three categories: normal, dyschardia, spondylolisthesis. For the second task, the categories dyschardia and spondylolisthesis were merged into a single category that is labeled as abnormal. Thus, the second task contains in classifying patient as belonging to one of two categories, normal or abnormal. Attribute information. Each patient is represented in the dataset by 6 biomechanical attributes that are derived from the shape of and orientation of pelvis and lumbar spine in this order: pelvic incidence, pelvic tilt, lumbar lordosis angle, sacral slope, pelvic radius, grade of spondylolisthesis. The following convention is used for the class labels: dyschardia is DH, spondylolisthesis as SL, and normal is NO, abnormal is AB. For more information about this dataset, see the vertebral column dataset webpage. Dataset attributions. This dataset was obtained from Dua et al. From University of California, School of Information and Computer Science. So for the lab setup, because this solution is split across several labs in this module, you run the following cells so that you can load the data and train the model to be deployed. Note, the setup can take up to 5 minutes to complete. Importing the data and training, testing and validating the model. By running the following cells, the data will be imported and the model will be trained, tested and validated and ready for use. Note, the following cells represent the case steps in the previous labs. In order to tune the model, it must be ready. Then you can tweak the model with hyperparameters later in step 2. So we have a bucket ID in here, and we are importing our libraries. So after that, the following cells takes approximately 10 minutes to complete. Observe the code and how it processes. This will help you to better understand what is going in the background. Keep in mind that these cells complete all the steps you did in the previous labs in this module, including importing data, loading data to data frame, splitting the data to training and validation test datasets, uploading the split datasets to S3, training, testing and validating the model with the datasets. So we have defined a function to plotting the rock the diagram. It has some you know, performance metrics defined. So for example, we have first defining the true negative, true positive, true negative, false positive, false negative, true positive values, and we are computing the sensitivity, specificity, precision, negative predictive value, fallout or false negative, false positive rate or false negative rate, and false discovery rate. Overall accuracy is also computed using this function defined in here, and also we are plotting our rock in the matplotlib. So these are some matplotlib commands to you know, draw the plot. So we have another function definition in here. It is plot for plotting the confusion matrix. We have test labels and target predicted labels. So after that, we are getting the dataset from this link in a zip format, and we shall be extracting it in order for us to then put it in a pandas data frame. After that, we are labeling our well, actually we are mapping our labels. Abnormal would be 1 and normal would be 0 using a class mapper. So that's straightforward. So we have already done these steps. I am just going through them one by one. So we are moving the last column to the first column, because the last column in the dataset was the labels, and for our model to predict the for our model to train, we need to move our labels into the first column position. So that's it, and we have train, test, validate splits in here, and we are using stratify to have a uniform split, and we have a prefix as lab3, and we have file names in here. So we have a upload s3 csv function definition in here, and we are using that function to upload our train, test and validate files, well, our data frames into files in here. So we are retrieving a container. It's an XGBoost algorithm, and it has a hyperparameters defined like so. So after that, we have S3 output location also defined, and we are getting our XGBoost model, and we are setting our train, validate and data channels. The validate data channels is used for training purposes. After that, we use the train channels, data channels, to train our model. So we have a batch defined in here. We are getting the test data as batch and uploading it. After that, we are using a transformer to make a batch transform, which means we are basically predicting our test data in here. So we have a you know, transform in here. Firstly, we are setting our transformer incidence to, after that we are using that to predict our batch. So we are waiting for it to finish. You can see the logs in here. So for the statistics of the model, before you tune the model, re-familiarize yourself with the current model's metrics. The setup performed a batch prediction, so you must read in the results from Amazon Simple Storage Service, Amazon S3. So from the S3, we are getting the target predicted values. We are using a binary conversion to convert our predicted values into binary, and we are extracting actually the labels from the test data. So we have test labels defined that way, and we also have the target predicted binaries in here, and we are using the plot confusion matrix function defined in the previous cells to plot our confusion matrix, plot the confusion matrix and the receiver operating characteristic curve for the original model. So this is the original model's confusion matrix. It has 7 true negatives and 19 true positives, and it has 3 false positive and 2 false negatives. So we are plotting the rock, and we have these performance metrics also: sensitivity, specificity, precision, negative predicted value, false positive rate, false negative rate, false discovery rate, accuracy, and validation AUC. So we have our rock curve in here. So our main goal is to maximize the area under the rock curve. So that way we have a better balance between, sensitivity and specificity at the same time. So we have also true positive rates in here, false positive rates in here. Also we have our threshold in the red line. So we are now construct a hyperparameter tuning job. A hyperparameter tuning job can take several hours to complete, depending on the value ranges that you provide. To simplify this task, the parameter used in this step are subset of recommended ranges. They were tuned to give you good results in this step without taking multiple hours to complete. For more information about the parameters to tune for XGBoost, see Tune an XGBoost model in the AWS documentation. So, because this next cell can take approximately 45 minutes to complete, go ahead and run the cell. You will examine what's happening and why these hyperparameters ranges were chosen. So from let's see in here, AWS documentation, we have recommended ranges for our hyperparameters defined in here for XGBoost algorithm. Since it might take a few hours to complete, we have a little bit simpler hyperparameter ranges. So from SageMaker tuner, we are importing importing the integer parameter, categorical parameter, also continuous parameter, and hyperparameter tuner. So we are getting a SageMaker estimator object, and it has a container, and it has a role defined. So instance count is 1. This is for parallel computing. If you increase the instance count, you are hiring more computer power, computer instances, I mean, to compute the models. For example, if you set the instance count as 5, that means 5 different models with different 5 different XGBoost models with different hyperparameters would be trained on 5 different computers. So that's a really good solution, because hyperparameter tuning takes too much time. So we have an instance type definition in here. You can also increase the power of your computer that you hired from changing the instance type. So output path is defined in here. Also we have a session in here. So after that we are setting some parameters that are not that important maybe, but well, we don't need to hyperparameter tuning. We don't need to define hyperparameter tuning jobs for these hyperparameters, because for example, number of rounds, objectives, and evaluation metrics, we are statically defining these hyperparameters. Well, you might also include some of these into your hyperparameter tuning jobs as well, but in this lab these are set as static, so it doesn't change. These hyperparameters will stay in other trained models as well. So we have hyperparameter range definitions in here. We have a continuous parameter of alpha values, which is from 0 to 100, and mean child weight as a continuous parameter as well, from 1 to 5, and we have subsample, and it's a continuous parameter between 0.5 and 1, ETA for another continuous parameter 0.1 and 0.3, and we have a number of rounds defined as from 1 up to 50, and it's an integer parameter. Well, actually there are number of parameter definition in here and also in here. Well, I think that means that we also tuning the number of rounds. So we have objective metric name, validation error. We have objective name is minimizing the error. Yes. This means the validation sets error, I guess. We are trying to minimize the error of the validation, error of our model's performance on the validation test. So we have a tuner objective, and here we have a hyperparameter tuner, and it's using our XGBoost object, estimator object. We have this defined in here, and it uses objective metric name. This is the objective metric, and hyperparameter ranges defined in here. Maximum jobs 10. This means that it will stop after maximum of 10 different hyperparameters set. So this will make it so that 10 instances of our model would be trained. Well, you can also say we will train our model in 10 times with different hyperparameter values. So if say so you might think that how it finds the optimum hyperparameters. Well, it for example, it looks for a alpha value of 50, let's say. If it performed well, that means the hyperparameter range for alpha value should be similar to 50, close to 50, and if it is not that good performance, that means it is not the alpha value shall be a little bit far from the 50. Maybe it's 70 or 80, 90. It might change. So we have max parallel jobs as defined 1, and we have objective type is defined to minimize our goal, to minimize the error. Early stopping us automatically early stop our model. So we are using the fit method for the tuner and passing the data channels, and CLS metadata is set as false. So we are waiting our tuner to finish up. After that, first you will construct the model that you want to tune. So we are constructing our estimator model. This is the model that we want to tune, and we also have defined its initial hyperparameters in here. Some of the hyperparameters actually. Notice the eval metric of the model was changed to error at 0.40 with a goal of minimizing that value. Error is the binary classification error rate. It is calculated as number of wrong cases divided by number of all cases. For predictions, the evaluation will consider the instances that have a prediction value larger than prediction value larger than 0.4 to be positive instances and the others as negative instances. Next, you must specify the hyperparameters that you want to tune in addition to the range that you must select for each parameter. The hyperparameters that have the largest effect on XGBoost objective metrics are, we have alpha value, minimum child weight, subsample ETA, number of round, as these are hyperparameters of our XGBoost model. So the recommended tuning range can be found in the AWS documentation from Tune and XGBoost model web page. We have also visited this page. So let's continue. You must specify how you are rating the model. You could use several different objective metrics as a subset of which applies to a binary classification problem. Because the evaluation metric is error, you set the objective to error. Okay. Finally, you run the hyperparameter tuning job, and we have also explained these. Wait until the training job is finished. It might take up to 45 minutes. While you are waiting, observe the job status in the console as described in the following instructions. To monitor hyperparameter optimization jobs. In the AWS Management Console on Services menu, choose Amazon SageMaker and choose Training Hyperparameter Tuning Jobs. You can select the status of each parameter tuning job, its objective metric value, and its logs. After the training is finished, check the job and make sure that it completed successfully. And we have also described our tuning job, and it is completed. So investigating the tuning job results. So now that the job is complete, there should be 10 completed jobs. One of the jobs should make a marked as the best. One of them is best out of 10. You can examine the metrics by getting hyperparameter tuning job analytics and loading that data into a pandas data frame. So we are getting the hyperparameter tuning job analytics from SageMaker.analytics. So after that we have tuner analytics from that function. When we are converted into the data frame, pandas data frame, using that data frame method, and after that we have sorting the tuning job analytics by the final metric value. So and we are final objective value we have sorted in that way. So we are showing the detailed analytics for the top 20 models. This since we have 10 models, this can be 10 actually. So well, I don't know why it is saying 20, but so you might see that we have 10 jobs completed, and final objective value we have maximum is in here and minimum is here. So since our objective was to minimize and we are trying to minimize the error rate, so and you should be able to see the hyperparameters that were used for each job along with the score. You could use those parameters and construct a model, or you can get the best model from the hyperparameter tuning job. Attached tuner, hyperparameter tuner, attached tuner, latest tuning job name, and the best training job was the latest one, I guess. And well, actually this one is performed better, I guess. So I don't know why it says the latest tuning job, but and from SageMaker estimator you're importing the estimator, and we are attaching the best training job. That way we have a trained model in here, and we are constructing a model. So then you can that way we are downloading the training image. So yeah, instead of going like For example, the 8 training is the best one, let's say. Well, instead of going like its hyperparameters are, for example, for each alpha value is this, and ETA is this, and minimum child weight is this. Let me train a new model using these parameters. No, this is not a good practice. We have already trained this model. We can, extract this model from the hyperparameter tuning job directly. We don't need to train it again using these parameters. So that's what we are doing in here. We are simply getting the estimator from the hyperparameter tuner. So then you can use the transform method to perform a batch prediction by using your test data. Remember that the testing data is data that the model has never seen before. So we have batch definitions in here. These are the file locations, file paths, you may say also, and a XGBoost transformer. Then yes, we are constructing a transformer object in here. After that, using the XGBoost transformer object, we are using a batch transformation to predict our test data. And we also wait for it to predict them. So after that, we have best target predicted values. This is the best model, and we are getting the target predicted values, and we are using a binary conversion again. So and after that, we have test labels, and we have best target predicted binaries, and we have using a confusion matrix to visualize that. So as you can see, we have now 20 true positives and 5 true negatives. In the previous case, let me show you, we have 19 true positive and 7 true negative. So and we have now plotting the ROC chart. We have some performance metrics in here again: specificity, sensitivity, precision, negative predictive value, false positive rate, false negative rate, false discovery rate, accuracy, and validation AUC as defined. And you now can see the area under the curve of the ROC curve is a 0.73, and let's see the previous one. It is 0.80. So how do these results differ from the original? Are these results better or worse? I would say that this model is worse, interestingly, because it has less area under the curve. This is one point, and the other point is it has a worse confusion matrix, because we had 7 true negatives and 19 true positives, whereas in here we have 20 true positives and 5 true negatives, and this is worse, I might say. So for an answer to this question, I might say the hyperparameter tuning job performed worse compared to the previous model that we had. Well, I might say that since these data sets were trained beforehand, the values that are given in the previous model, the hyperparameters, would be optimized. That's one thing that I might say. So, and you might not always see an improvement. There are a few reasons for this result. The model might already be good from the initial pass. Yes, that's the case for our case. What counts as good is subjective. This is really important. Well, do you want to, truly predict the abnormal cases, or do you want to also truly predict the normal cases? You have a trade-off between those two. So it is subjective. You don't have a large amount of data to train it. Yes, this is the really important reason as well. So you are using a subset of the hyperparameters tuning range to save the time in the step. Yes, this is also the case. Increasing the hyperparameter range, that's one solution, as recommended by the documentation, and running more than 30 jobs will typically improve the model. However, this process will take 2 to 3 hours to complete. Yes, and congratulations, you have completed this step, and you can now end the lab by following the lab guide instructions. That's all. That's it for today. Thank you for listening, man.